Well, already every non-empty set of non-negative integers has a least element. That is, if S is a subset of, so I have taken non-negative integers, okay, as per dividend pattern. So we can just include non-negative means 0 is also included. Okay, 0 together with the positive integers. So it's like this. So if S subset of n union 0, okay, and S is not equal to 5. Okay. If it is an empty set, we cannot find out such an least element. Empty set doesn't have any elements. Okay. So if S subset of n union 0, okay, n is the set of natural numbers, union with singleton 0, okay, and S is non-empty, then there exists an element A inside S such that, so A is the least element. So A is less than or equal to, so least element means it is smaller than every other element. Okay. So A is less than or equal to X for all X inside S. Okay, that is the meaning. A is smaller than every other element of S. Okay. Right. So it is the smallest. Okay. So it has the least element. It's the least element here. It will be unique. There cannot be two least elements. So if A and B are two least elements, okay, then A is less than or equal to B. No? Suppose A and B are two least elements. So least element satisfies A less than or equal to X for all X. So if A and B are two least elements, then A should be less than or equal to B. B also should be less than or equal to A. Okay. So ultimately A should be equal to B. Okay. So the least element is actually unique. Right. So we can also write it as the least element. Okay. So this is what is meant by the well ordering principle. Okay. So it is regarded as one of the basic principles of mathematics. Okay. So we will regard this as a god, one of the gods of mathematics. Okay. Right. So using this, we will prove the principle of mathematical induction, and we will also prove the division algorithm. Okay. Right. Using this concept, we will prove division algorithm. So this is where we begin our number theory, the division algorithm. Okay. So let us take it formally. Okay. So given integers a and b with b greater than 0. Okay. So b is positive. So there exists unique integers q and r such that a is equal to b q plus r, okay, where r satisfies this restriction. Okay, 0 less than or equal to r, strictly less than b. Given integers a and b, there exist unique integers q and r such that a equal to bq plus r. Come on, 0 less than or equal to r, strictly less than b. Okay. So this is the division algorithm. So if we start with two integers with one of them positive, so later on we will see that this one of them has to be just non-zero. we can divide by negative numbers also. Okay. So we'll see that as a corollary. So for proving, we'll take this b to be greater than 3. Okay. Then we can find the quotient and remainder. Okay, this is the quotient and this is the remainder. Okay, so they will be unique. Okay. Only in one way you can write. Okay, because we have given this restriction. So with that restriction, we can prove the uniqueness. Right? Given integers a and b with b greater than 0. There exist unique integers q and r satisfying a equal to bq plus r. Okay. The integers q and r, are called the quotient and the remainder. Okay, because they are unique, so we write it as the remainder in the division of a and b. Okay. The integers q and r are called the quotient and the remainder in the division of a and b. Okay. So in your school days also you have done this. If you remember, you were taught division. Okay. So, say 200, say 20, 215. Divide this by say 4. Okay. So how do you do it? 4 5 is 20, 1, 5, 12. Okay. So this part is the remainder, and after that you were asked to check if this is correct. Okay. So you had something like this: dividend equal to divisor into. That is nothing but the division algorithm. Divisor into quotient plus. So if you get something bigger than 4 here, okay, if I write 4 to the 8 and here I write 7, okay, then your division is incorrect. Okay. Your division is incorrect. Okay. But even then, this will also satisfy 215 equal to 4 into 52 plus 7. Okay, this will be satisfied. But the problem is this remainder comes out to be greater than the divisor. Okay, so that is not allowed. If I want to say that the division is a correct one, then this remainder should satisfy this inequality. Okay, and it should lie between 0 and the divisor. Okay. So this is incorrect, but this one is correct. This is correct. Okay, this is the correct division. Okay. So how to prove this using the well ordering principle that we have stated. Okay. How to prove this using well ordering principle. Okay. So we start with the proof with this. Let us consider the set. Okay. So what we do is we take this PQ to the other side and consider this set A minus PQ. Consider the set S equal to A minus BX such that all these are integers. A, B, X. So that X is an integer. X is an integer. So I don't have to write this. So that A minus BX is an integer, and then how did they write? X is an integer. Just write it. X belongs to and a minus bx. So this q can be negative also. Okay, it is not necessary that q should be positive. Q can be negative also. So x is an integer and a minus bx is greater than or equal to 2. Okay. So we have taken a set of what? Non-negative integers, because a minus bx, okay, this is greater than or equal to 0. Okay. We have considered all those a minus bx for which a minus bx is greater than or equal to 0. Okay. So it is a set of positive integers, okay. Non-negative integers, sorry. This is a set of non-negative integers. Okay. So let us consider the set as equal to this. Okay. So to apply division algorithm on this, to apply well-ordered principle on this set, what else do I need? It is a set of non-negative integers. That is, by definition, it is an integer. Okay. What else do I need? No. To apply well-ordered principle, what is well-ordered principle? Every non-empty set of non-negative integers, okay, has a list element. So this here I am sure that it is set of non-negative integers. Okay. Together with that, what else I need? I need to confirm. It should be non-empty. Whether there are some elements inside this set or not. Okay. This is what we have to confirm. Okay. Oita kibabe confirm korba? Can you find out some elements here in this set? Try to find out some elements inside this set. Try finding out some element. Okay. Give at least one element inside this set. See, if you take x equal to 0, then a minus b into 0, which is equal to a. Is it an element inside this set? Huh? This one? Is it an element inside this set? Huh? Yes or no? No, we are not sure. Because an element inside this set will be non-negative, greater than or equal to 0. So here this element is equal to a, and a is given to be an integer. Okay, that may be negative also. We are just given b is positive. Okay, so we are not sure whether a is an element inside this set or not. So if a is greater than or equal to 0, then it is inside this set. Okay. If a is negative, then this element is not inside this set. Okay. So if a is negative, you try to find out some elements inside this set. Suppose a is less than 0. Can you find out some elements inside this set? Cannot find out. What?
Then x should be negative.
Huh?
Then x should be negative.
Yeah, x should be negative.
And mod of b should be greater than a.
Mod of
B should be greater than a.
mod of b should be greater than a. Okay. So this is one. But mod of b may not be greater because a and b are any integers. Okay. It may happen that a is minus 1 and your divisor is 5. It may happen that way. So the restriction will not be on mod b and a. The restriction will be on x. Okay. Mod x will be greater than something. Okay. So you try to find out some integer. Almost you are close. Almost there. Which number, if I take a number here, which number will be, for which number this will be a positive? For which number this will be positive? See, you have mod of a is always greater than or equal to a. No? Mod of a, this is always greater than or equal to a. Okay. So from there also you can conclude something. B is a positive integer. Okay, so if you multiply both sides by b, then b into mod of a. Okay, this will be greater than or equal to a into b. Okay. So from there you can have some idea. If I take x to be,
X equal to mod.
Mod A or what? Mod A or if I take x to be mod of A, then for this if A is negative, okay, then what will happen to that? If A is negative, then x is mod A. So what will be the value of mod A for x A to be negative? For negative value of A, what is the value of mod A?
Minus of minus A.
Minus of
Minus
not minus of minus A, it's minus A. If what is mod x? Mod x is x if x is greater than or equal to 0, and minus x if x is less than 0. Okay. So if I take x as mod A, then your this value will be minus A. Okay. X will be equal to minus A. In that case, what will be this value? It will be A plus A into B. A plus A into B. So from there, can you identify whether it is positive or negative? I want this to be a positive quantity. Okay. Now, which value of x should I take so that I get at least one positive number? It is sufficient to get one positive number. Okay.
So x
There is
equal to
no
minus
x equal to
minus A.
minus A. So in that case, what I get? A minus B into minus A. Okay. So this will give us A into
1 plus B.
1 plus B.
And B is greater than 0.
But again, you see, I have taken A to be negative. So A into 1 plus B is again negative.
Negative.
So x equal to minus A is also not working. Try to think. X equal to A divided by this we cannot write. We are working in the with only integers. Okay, it may happen that your A is 3 and B is 2. So x is not an integer in that case. X equal to 3 by 2. It's not an integer. Okay. So try to see something else. Mod of B, this is also greater than or equal to 1 because B is a positive integer. Mod of B is greater than or equal to 1. That is also correct. A into mod B, this is also greater than or equal to A. Okay. If my question is if A is positive, we can take x equal to 0. Okay, no problem. Then this A. If A is greater than or equal to 0, then x equal to 0 will work. This A is an element inside this set. If A is negative, what element should I take? You try with some values. Okay. Suppose I take A is minus 3 and B is 2. Okay. Then for which value A minus Bx will be greater than or equal to 0? Which value of x? Okay. Just try to think like that. Suppose A is minus 3 and B is 2. Then what should I take as A minus Bx? Means, what should I take as the value of x? So that A minus Bx becomes greater than or equal to 0.
Minus 2.
If you take x equal to
Minus
x equal to what? Minus
2.
2. Okay. Then you get something like x equal to this is A minus, this will be minus 3 minus plus 4. Okay. So this will be equal to 1. Okay. So x equal to minus 2 is working in this case. Okay. So that way you try to think what x should you take so that this becomes positive.
X equal to A plus 1. X equal to A plus 1.
X equal to A plus 1. Okay. So it is A minus B into A plus 1. So what is that? A minus A into 1 minus B minus B. Okay. So here also it's not a guarantee that x is that this quantity is positive. What value should you take? If A is negative, what value should you take? So that this becomes positive. Hmm? See, what is A minus A plus B into modulus of A? Modulus of A. If A is positive, it is A plus B into mod A is A. Okay, so this is actually A into 1 plus B. Okay, so A is positive, 1 plus B is positive, no problem. If A is negative, then what happens here? A plus A minus B into A. Okay, so it is like A into 1 minus B. So what can you say about this number? A is negative. I am saying that A is negative. So what about this number? A into 1 minus B.
1 minus B तो surely positive or negative ना यदि
1 minus B.
surely positive or negative ना because यदि B greater than 0 है ते negative होते पारे positive होते पारे यदि B greater than 1 है surely अगर होता
B is greater than 0 and B is an integer. So B is actually greater than or equal to 1. B cannot be something between 0 and 1. Okay, that is the thing. A and B are both integers. Okay, so whenever I write B is greater than 0, this actually means that B is greater than or equal to 1. Okay, because B is an integer, I can write that. If B is a real number, I cannot write. B greater than 0 may imply that B is 0.5, 0.1 like that. Okay, but since B is an integer, there is no other possibility. The next possibility is B will be greater than or equal to 1. Okay. So what can you say about this quantity 1 minus B?
greater than equal to 0
No, B is greater than or equal to 1. So 1 minus B is less than or equal to 0. Okay. And we also have A negative. Okay. So A into 1 minus B, if I multiply by a negative quantity here, the inequality will get reversed. Okay. So A into 1 minus B is actually greater than or equal to B. Okay. So in the earlier case we had seen if I take x equal to mod A, it's not working. But if I take x equal to minus mod A, okay. If I take x equal to minus of mod A, okay, then it works. For A positive also this is positive. Non-negative, or A negative also, this is non-negative. Okay. So if we take x equal to minus mod A, okay, everything works here. Okay. So we will take something like this. So the hint is this. The hint that I had given you, modulus of A, this is always greater than or equal to A. Okay. Modulus of A, this is always greater than or equal to A. Okay. And B is a positive quantity. So B is greater than or equal to 1. So B into modulus of A. This will be always greater than or equal to modulus of A. Okay, and then this is also greater than or equal to A. So ultimately, no matter what happens to A, positive or negative, this quantity is a positive quantity, which is the absolute value of this quantity is greater than or equal to A. Okay, so this sum. The sum of this and this is always greater than or equal to 0. Okay. So from here it will follow. So if you take x equal to minus mod A, then we get at least one element here inside this set. That is S is non-empty. Okay. Of course, there are other values also for which S is non-empty. You take anything greater than mod of A. Okay. You take any positive this x to be minus of anything that is greater than mod of A. Okay. So then also you will get an element inside this set. Okay. So actually there are infinitely many elements inside this set. Okay. Clear? So we will just justify this with our result. Okay. So let us consider this set. Then minus of mod A, okay, we have A minus Bx is equal to what? A minus B into minus of mod A, okay, minus of mod A. So this is actually equal to A plus B into mod A, okay, and this is greater than or equal to, just now I told mod A is greater than or equal to A, so B into mod A, this is also greater than or equal to B into mod A is greater than or equal to B, okay, sorry, B is greater than or equal to 1, so if you multiply both sides by mod A, so B into mod A, this is also this is always greater than or equal to modulus of A, okay, so this is what we are doing. So this is greater than or equal to A plus B into just mod A, okay. So in the this side you can write, since B is greater than or equal to 1 implies B into mod A is greater than or equal to mod A, okay. So this is the right. So B is greater than or equal to 1, so B into mod A, so instead of this I can replace by this, so this will be greater than or equal to this quantity, okay. But this A plus mod A, this is always greater than or equal to 0, because mod A in magnitude, the magnitude of this is the absolute value of this is greater than this always, okay. So when you add them, this will be always greater than or equal to 0, okay. So in fact A plus mod A is either if A is positive it is twice A, greater than or equal to 0. If A is negative, it is actually 0. Okay, so there are only two possibilities. For A plus mod A, there are only two possibilities. Either it is 0 or it is exactly equal to twice A. Okay, so in both cases it is greater than or equal to 0. So a number plus its modulus is always non-negative. Okay, so this is always greater than or equal to 0. So actually whatever we have done, we have found out an element inside this. Okay. So thus A minus B into minus of mod A, okay, is an element. So this is an integer, is an element inside S. Okay. So hence S is non-empty. Okay. S is not equal to 5. Okay. S is a non-empty set. Right. So we have got a non-empty set of non-negative integers. Okay. By definition of this set, it is a set of non-negative integers. Okay, and now just now I have proved that it is a non-empty set. It is a non-empty set. So we can apply the well ordering principle here. Okay. Hence, thus S is a set of is a non-empty set of non-negative integers. Non-negative integers. S is a non-empty set of non-negative integers. So by well ordering principle, there exists the least element. There exists S has the least element. Okay, S has the least element. In it, say R. Okay. So we denote that least element by R. Okay. R is the least element. So here exactly the well ordering principle is applied. Okay. We have got a non-empty set of positive and non-negative integers. So we can apply the well ordering principle that this set will have the least element inside it. Okay. Least element है वही set में 3 था. Okay. It will be inside the set. Okay. So by well ordering principle, S has the least element in it. Say R. Okay. So suppose R is the least element. Okay. but R is an element of this set. Okay, but how do the elements of this set look like? Elements of this set look like A minus B into some quantity. Okay, so since R belongs to S, so there exists Q inside Z. Okay, so now we will denote this X by Q. Okay. So that there is Q inside Z such that A minus BQ is equal to R. Okay. So that is A equal to BQ plus R. Okay. R will look like this. Okay. A minus B into some integer. Okay. So we denote that integer by Q. Okay. So there exists a Q inside integer such that A minus BQ is R. So A equal to BQ plus R. So till now we have got this expression, but we need something more. What do I need? I need that R should lie between 0 and B, strictly less than B. Okay. R cannot be greater than or equal to B. Okay. That is what is left. Okay. What happens if R is greater than or equal to B? Okay. So R is greater than or equal to 0. This is obvious because R is an element inside this set. Okay, what are the elements inside this set? They are non-negative integers. So since R is an element inside this set, R is greater than or equal to 0. One part is obvious. Okay. Right. So now we will see if R is strictly less than B or not. Okay. If R is not less than B, then what will happen? Okay. So this is what we will see now. Now R belongs to S, so this implies that R is greater than or equal to B. Okay, so this part is obvious. Suppose that R is greater than or equal to B. Okay. I want to show that R is strictly less than B. Okay. So to the contrary, I suppose that this R is greater than or equal to B. Then what will happen? Then this R minus B, this will be greater than or equal to 0. Okay. If R is greater than or equal to B, then R minus B will be greater than or equal to 0. Okay. So look at this element. R minus B is greater than or equal to 0. Then so look at this element A minus B into Q plus 1. What is this? This is equal to A minus BQ and minus B. No? Okay. I can write this A minus B into Q plus 1. It can be written as A minus BQ minus B. Okay. So here A minus BQ is what already we have seen, that is R. Okay. So this is R minus B. No? A minus BQ. So instead of A minus BQ, I can write R. So this is ultimately R minus B. Okay, clear. And what is R minus B? Just now we have seen. This is greater than or equal to 0. Is it? R minus B is greater than or equal to 0. Okay. So this means what? What does this mean? This is an element of the form A minus B into some integer. And it is also non-negative. So this is an element inside which set? This is an element inside S. This is an element inside S. Okay. So A minus B into Q plus 1. This is an element inside S. Okay. Now which element is smaller? This is smaller or that is smaller? A minus B. This is greater than or equal to 0. Okay. So this element is actually R minus some positive integer. Okay. So this is an element inside S, but A minus B into Q plus 1. This is equal to R minus B. And can I write this is strictly less than what? R. Okay. This is a positive number. Huh? and from R I subtract a positive number, then whatever I get, it is strictly less than R. No? You take the difference of these two, R minus B, so that you get B, which is greater than 0. Okay? So this quantity is strictly less than R. Okay? So we have got an element inside S which is smaller than R. Okay? So what is the problem? Problem ta kun jagah pe R is the least element. Okay, so we have got some element which is smaller than the least element, so that cannot happen. Okay, that means this cannot happen. R cannot be greater than or equal to B. Okay. If R is greater than or equal to B, then we get that R is not the least element. Okay, but we have already taken R to be the least element. Okay, that is the problem. So A minus B into Q plus 1 is in S, but A minus B into Q plus 1 is R minus B, which is strictly less than R. Okay, this contradicts the fact that R is the least element. Okay. R is the least element of S. Okay. Least element of S. Okay. So R should be strictly less than B. Okay. So this cannot be correct. R greater than or equal to B. Okay. So let me write it in 2 lines. Hence, our assumption that R is greater than or equal to B is incorrect. This is an incorrect assumption. Incorrect. Therefore, R should be strictly less than B. Okay. So that is 0 than or equal to R less than. Okay. So we have seen that this inequality is also satisfied. A can be written as BQ plus R, and this inequality is also satisfied. Okay. Right. So we have proved the existence part. Okay. So the existence part is proved. Means we have proved the existence of 2 integers Q and R, which satisfy. The existence part is proved. Okay. That is, what is the meaning of this? Meaning is this. That is, so there exists. We have already proved that A equal to DQ plus R. Okay. Existence. And now I have to show the uniqueness part. I have to show that the Q and R that I get, they are actually unique. Okay. So now we deal with the uniqueness of Q and R. To show that Q and R is unique. Okay. So suppose that they are not unique. Okay. Suppose that I have done the calculation and I have got Q and R. Somebody else has done the calculation and he has got Q dash and R dash. Okay. Then to show the uniqueness, what should I show? I should show that Q is equal to Q dash and R is equal to R dash. Okay. This is what I have to show. So suppose there exist integers Q dash and R comma R dash such that A equal to B Q plus R, 0 less than or equal to R, strictly less than B, and A equal to B Q dash plus R dash, okay. 0 less than or equal to R dash less than B. Okay. Q already we have seen. Suppose there exists integers. Existence of Q and R already we have written. Okay. Just we can write about Q dash and R dash. Okay. Okay. 1 less than b and 0 less than or equal to r dash less than. Then what you can see from here then what is it? bq plus r will be same as bq dash plus r dash.